Okay, so this will be a complete change of pace from today's exciting discussion. This is all very boring stuff, no new physics, nothing you didn't learn in second year physics, and in the much more mundane world of hundreds to millions of newtons rather than the world of micronewtons. And it really is only a little of this is the new work that I've been doing. A lot of what I'm doing is evangelizing work that others have been doing over the last few decades. And I think that there's one real carry-away lesson I want you all to carry away from this discussion. It's, you don't have to resort to pushing on the quantum vacuum or pushing on the fixed stars or the preferred reference frame. Space is not empty. And the matter that is in it forms a perfectly workable medium for many forms of propulsion. So the beginnings of this for myself come when I discovered John Slow and company's work at University of Washington on the plasma magnet, which I'm going to go into some detail discussing. I came across it in 2009 when I was on a committee that was trying to figure out if NASA had access to really game-changing technologies. And I got extremely excited about it, but it took me until 2018 to figure out how to make some missions out of it. So I'm going to run through some of the missions that you can do with just the drag device, the plasma magnet. I'm going to talk about another class of stuff that has been published. And then at the end, I'm going to run off of the slides and just tease some of the work that I've been up to that I'm still preparing for publication. Like everybody else, this year has not quite gone according to plan. So some of the draft material that I'd hoped to have published this year is still in preparation. So what the plasma magnet is, first, historically, I think part of the reason this is not as well known as I think it ought to be, is it was conceived by the same group and about the same time as another propulsion system called M2P2. M2P2 is a rather exotic plasma confinement technique that people other than its inventors probably think doesn't work. And so since the same group was working on these two different systems, I think the community got the two of them confused in their mind and dismissed the plasma magnet, which is really quite different in its physical principles and much better grounded. What the plasma magnet is, very briefly, is if you're familiar with how an electric motor works, you have two or more coils on the stator of an electric motor. And those coils are energized in series, and that makes a rotating magnetic field. If you have an electric motor, there's then a magnetized object that's free to rotate inside those coils, and that's drug around by the rotating magnetic field. That's what makes the torque, and that's what makes electric motors work. Now throw the rotor away and put that stator in a conductive medium, like liquid mercury or seawater or the plasmas that you find throughout space. What you'll find is that that rotating magnetic field now, as long as it is rotating more slowly than the electrons in the plasma can follow it, it will drag the electrons around by the motion of that magnetic field. Okay, so what? Well, now you've made a current. You've made a current in the plasma that is outside of, exterior to, the confines of the coils that you made the magnetic field out of. So the really interesting question is, what's the radius of that resulting current loop? And what John Slow found, both theoretically and experimentally with tests in vacuum chambers with simulated winds, is that as you all probably well remember from college, or if you've ever worked in high field magnetic systems, you've experienced this. The magnetic field in a loop of current repels itself. That's why high field magnets need support, so that the coils don't blow themselves up. If that current is made of unconfined electrons that are just in the plasma, they're not in a wire, that loop of current expands. And that loop of current will expand until the magnetic field pressure, which drops with the increasing radius of the expansion, is balanced by some other source of pressure, whether that be an external magnetic field or whether that be an external static pressure in the plasma. But in practical terms, in most applications, what matters is the dynamic pressure, the pressure of the wind speed of the plasma that you're passing through. Usually in the space plasma cases of interest is totally dominant over the other sources of pressure. That means you get from quite modest apparatus, scale devices where the driving coils are on the range of meters to tens of meters of radius, with quite practicable energizing forces, kilowatts. You can get magnetic fields in the solar wind plasma with radii of tens or hundreds or even thousands of kilometers. So that even though the solar wind dynamic pressure is quite modest, on the order of a nanopascal, you're intercepting enormous cross-sectional areas of that space plasma with, tens or hundreds of kilograms of apparatus. Back at the envelope calculations, I'm going through with the AIAA Technical Committee on practical interplanetary propulsion right now. And so far, neither I nor anybody else has found the fatal flaw in John Slow's original calculations. You're talking about achievable accelerations in the solar wind plasma that are on the order of a fraction of a meter per second squared, like a tenth of a meter per second squared. Which in the world of advanced space propulsion, it may not sound like much in terms of ground activities, but in the world of advanced space propulsion, that's screaming. The people who are doing things like electric propulsion would kill for a tenth of a meter per second squared. There's a reason why those guys have recalibrated themselves. They normally talk in terms of millimeters per second squared instead of meters per second squared. So this has a number of practical, so here's just some simulations, and this is the picture of John's result in the wind tunnel, validating the numerical models that he was doing. Truly, I wouldn't know what's left to do with this in terms of buying down the technology readiness level, except to fly it in space. It's been measured on the ground in a vacuum chamber with a simulated plasma wind made from an ion thruster, measured with a thrust balance. And you're not talking about micronewtons here, you're talking about newtons. So there's not a lot of mystery about it. You can measure it with a pendulum. I get the sense that there's a chat window going that I should be looking at here. Nope, I can't figure out how to pull it up. Oh well.
At the bottom of your screen, you see a little, of the 5 icons, there's one that says chat. You just click on that. You see it up?
There we go. No, he did not fix the Bussard ramjet. Magnetic fields make terrible scoops. In fact, the whole origin of the field of magnetic sailing goes back to Zubrin and Andrews when they were trying to work on making scoops for a Bussard ramjet and discovered that you just can't do it. Magnetic fields don't collect particles, they reflect them. So they make lousy scoops and great drag devices. And really the origin of this whole field only goes back to the 80s, or actually the 90s, when Zubrin and Andrews, I think, were the first to recognize that drag devices are propulsively useful. Parachutes and sails have a long history in propulsion. Not everything has to be a ramjet. And yes, the other question is this analogous to the plasma magnetoshell concept that people are looking at for doing aerobraking? And the answer is they're similar, not exactly the same thing, but they use similar physical principles. In the case of aero capture, you're trying to make a cloud of ions that collides with the neutrals in the atmosphere to make drag in a weakly ionized plasma. In the case of operating in space plasmas, you're talking about essentially a fully ionized plasma. There is no significant contribution of the neutrals. So far, I'm only talking about pure drag devices. So the pure drag device, this is what's in the prior art. Pure drag devices only make thrust in the direction of the wind. So as so far discussed in response to the question about orbital maneuvering, this principle so far will not maneuver you anywhere in orbit because you're inside the magnetosphere of the Earth. There's essentially no wind. On the other hand, once you get outside the magnetosphere of the Earth, you're in the solar wind. Now, if you don't know, the solar wind, depending on where you are in the solar system, blows, and it varies with time, but it blows between 300 and 750 kilometers a second. 350 to 700,000 meters per second, which in rocket terms is huge. Well, bear in mind the exhaust velocity of a locked hydrogen rocket is about 4,500 meters a second. So this is 100 times faster than that. So just by hoisting a sail, just by putting up a drag device, you can get going outwards from the sun. The only direction the wind blows is outwards from the sun, at speeds of hundreds of kilometers a second. I'll come back to tacking in the second half of the talk. That's 100, outside of the plane of the ecliptic, that's 120 astronomical units a year. Okay, that's the that's Voyager distances in a year. So that was all discovered in the 90s. And NIAC funded it all the way through phase 2, the old NIAC. Validated in wind tunnels, and when I came across this work, I was like running around with my hair on fire, going, "Why isn't anybody talking about this? You know, it's massively useful." Well, the problem is, while there are missions like a solar gravitational lens mission, like an interstellar precursor or interstellar medium explorer, there are missions where just going away from the sun is useful. There aren't that many of them. Most of the things that people would like to do involve also stopping. And there I got stuck. How do you stop when the only thing you can do is go away from the wind? Okay. So, but I will walk through a couple of things that you can do. This gets you 1,000 astronomical unit type missions with flight times on the order of 8 years. That'd be useful. They get you Neptune flybys in about 6 months. But for Mars, not so easy to do because you got to stop. So I'll skip on to that. But one thing I do want to put a little more emphasis on is interstellar braking. And in fairness, this is now the subject of some work I'm doing as a subcontractor to a NIAC activity that's currently funded that Jerry Jackson is the principal investigator for. The braking problem in interstellar flight is underemphasized. I was appalled at a recent conference when JPL folks got up and talked about their magical system for doing an interstellar precursor mission, and then they said, well, of course, if you brake, you have to square the mass ratio, as if the only way that one could brake was by propulsively braking. It's crazy to propulsively brake from interstellar speeds. You know, that's really expensive kinetic energy. You put a lot of effort into acquiring it. The last thing you want to do is double your delta V by repeating whatever it is that you did to get up to speed. So it turns out that at interstellar relevant speeds, however you get to them, say 10% of C or more, solar systems are really small. You know, the flight time across the solar system is hours. So you simply can't brake inside the heliosphere of a target star, even leaving aside, for example, that Proxima Centauri has a very small heliosphere. You have to brake in the interstellar medium. It's the only thing you got. But the plasma magnet and similar kinds of technologies are made to order for that. Because again, yes, the interstellar medium is thin, but at 10% of C, the dynamic pressure of it is actually higher than the dynamic pressure of the solar wind. So you can apply the same principle and get quite practical braking speeds. In fact, by playing some tricks I'll talk about in a little bit, I think you could actually ramp up to about 1 meter per second squared. which gets your braking speed from 10% of C down to about a year. So it's an eminently practical and important part of the interstellar propulsion problem that is underexplored. And one of the nice things about the NIAC that we're doing is we're going to go through a quantitative trade of the various braking technologies, which I will pass over lightly. There are more ways to do it than the plasma magnet, but the plasma magnet is one of the most intriguing. I got to figure out how to minimize this chat. There we go. I have the challenge that the chat window obscures my my next page button. There we go. Okay, so just a quick survey through braking technologies. The original magnet sail, Zubrin and Andrews. It's just a big loop of superconducting wire. The challenge is because the big loop of superconducting wire has to be big, it tends to be heavy, your achievable accelerations tend to be low. It works at very high dynamic pressure, so it may have a range of applicability that pairs with a plasma magnet. The E-sail is the electric analogy of the plasma magnet. It's a bunch of wires with carry a charge. The charge makes a depleted sheath, a device sheath, and that device sheath scatters the incoming ions. Works the same as the plasma magnet, except electric instead of magnetic. Has the drawback that you have to paper the entire zone of interest with the wires, so it's a great deal heavier than the plasma magnet is. And there's a nice paper that was published that's cited here if you want to go back and look at it, on how to combine the mag sail and the E-sail, because they work in different parts of the deceleration curve well. And then plasma magnet I have talked about, and I will talk about more, so I won't dwell on it. There's the citation to Slow's original paper. And electrodynamic tethers are, in essence, another way of doing the same thing, where you make a loop of current in the medium by forcing part of that current to pass through your wire. One last one I want to mention, because it's highly relevant to the second half of the talk, is plasma waves. Plasma waves is a field that Jim Gilland did some work on. I think there's a lot more that can be done here. I've already seen some evidence that there's a lot more pony in here. Briefly speaking, any wave in a medium carries momentum. And the amount of momentum that it carries is something to do with the group velocity of the wave in the medium. You know, we're all familiar with light pressure, where the thrust is the power divided by the speed of light. Speed of light being a big number, it takes a lot of power to get thrust from photon pressure. There are all kinds of wave modes that propagate in plasma. There's Alfvén waves, which are magnetic field tension waves. There's, I can't remember all the names of the wave modes. I mean, there's collective motions of the ions, there's collective motions of the electrons. And the interesting thing about that is, you know, those have very complicated group velocity versus frequency diagrams, because they're interacting with resonances that are in the plasma. By operating arbitrarily close to those resonances, you can make the group velocity almost anything you want. You can get awfully close to zero in some of those phases. It breaks down as you get too close to zero, because some of the effects that are normally neglected become non-negligible. But it's certainly plausible to think we could get plasma wave modes, the speed of which is down in the range of kilometers per second. This is relevant to braking, because that provides a means by converting the motion of the ship into stimulating the oscillations of the plasma. That kinetic energy of the ship is radiated away in the plasma. As braking, it's only one of the relevant fields, but it also forms what I would term as a propeller. You know, when you push on a medium, it obeys the propeller equation. Ideally, thrust equals power times your velocity in the medium. And there ain't no way to beat that without violating conservation of energy. So what you want in a propeller, if you want to use a propeller type drive, which plasma waves are, is you want a nice slow wave, because that means the minimum velocity of the wave is low. But they're kind of not very useful for achieving high speeds by pushing on the plasma. And that would be true for anything that pushes on something stationary, because the power requirement goes up as your speed goes up. Otherwise, you violated the law of conservation of energy. Even if you can push on a big, massive thing that you didn't have to carry with you. I'll skip that. Okay, so now this is more of my own work than a review of the great stuff in history. But the great stuff in history is great, you know. So I'm going to continue to evangelize for it, because I think it's, you know, as somebody I think commented in the comment, hundreds of kilometers a second for free, that ought to be good for something. My chat window just keeps vanishing. There it is. It is very useful for solar gravity lens mission. It's perfect match for solar gravity lens mission, because you don't have to stop, right? Solar gravity lens is a long line of focus. And solar gravity lens missions also, this is not widely appreciated, have to be cheap, because you can't move the telescope, right? You have to launch the imaging object opposite the sun of the thing you want to look at, very precisely opposite the sun of the thing you want to look at. So every single thing you want to look at is a different mission. So they have to be cheap. So the idea of a low mass ratio, low technology thing we could build right now that would get you out to the solar gravity lens in like 5 years of trip time is a match made in heaven for the solar gravity lens type of missions. And that's what I'm talking to the AIAA Technical Committee on Advanced Propulsion about right now. Okay, so how do you stop? Or how do you sail upwind, as I like to put it? Max, I'm Jeff at here. My email, in case anybody wants to get me afterwards, is jeff@greason.com. Very easy to remember. Okay. How do you stop is a problem that I was stuck on from 1999 to 2016, or 2009 to 2016. I just could not figure out a way to do it. Just to review, what's so exciting about the plasma magnet is when you're talking about advanced propulsion problems, it's really specific power more than specific impulse that is usually your problem. We have electric drives and things like that that have nice high specific impulse. But if the specific power isn't high enough, your accelerations are so low, you can't make effective mission use of those kinds of capabilities. What's exciting about the plasma magnet is the thrust power you're getting out of the solar wind is on the order of 10 to the 5th or 10 to the 6th times greater than the electric power you had to put into the coils to push the plasma around. Anytime you can get a factor of 100,000 or a million power for free, you should be paying attention in terms of advanced propulsion. So how do you stop? To answer that, I got to go back to some physics fundamentals. This again is just the propeller equation. This is how cars work, airplanes work, ramjets work, you walking down the street works. You know, your power is at least, it can be greater than, but it's at least your thrust times your speed against the medium that you're pushing on. And your thrust is the mass flow of that medium that you interact with times the change in velocity you impart on it, which is a number you want to be as low as possible. Rockets, the other thing we're all familiar with, you know, power is 1/2 thrust times exhaust velocity. This is just basic physics. All 100% efficiency, all 0 losses. This is the best you can do. Thrust is then the mass flow of rocket propellant times the exhaust velocity, which leads directly to the Tsiolkovsky rocket equation that you all know by heart. And sails and parachutes are kind of the third class of device. They actually use the same equations as propellers, only in reverse. The effective power is the drag times the airspeed. And that's power that you dissipate into the medium rather than power that you had to apply to the medium, because you're removing kinetic energy if you're a drag device. So this led, I was going to give up in 2016. I was just gonna, I couldn't find a way to do it. I said, I've tried everything, therefore it can't be done. I said, okay, before I do that, I should do his Wikibox and actually list all the things and make sure I've tried everything. And what I did is I realized I hadn't actually tried everything. I hadn't considered the possibility of collecting the power from the wind and carrying the reaction mass aboard the ship. Rockets, you carry everything aboard. Sails, everything is external. And propellers, you supply the energy, and the world around you supplies the reaction mass. I was pretty sure this was a terrible idea, but I hadn't tried it, and I was running out of ideas, so I tried it. And to my shock, it turned out to be incredibly productive. For derivations of this and all the equations following in the paper, they're all published in my JBIS paper, which is available from the British Interplanetary Society, or there's a copy of it hosted on the Tau Zero website. So any drag device is in principle a windmill, right? If you can, I'm just struggling. I've tried to explain this so many ways, and almost nobody gets it the first time. So I will say, if you listen to this and you don't get it the first time, I encourage you strongly to sit down and play with the equations yourself. Almost everybody who's actually got this came to me the next day and said, last night I worked out the equations myself in my hotel room, and now I see what you're getting at. I haven't found a better way to explain it yet. But if you think about the wind pushing on a plate or a parachute or something like that, right? Mechanical work is done only in proportion to how much motion the plate or parachute goes through. It's somewhat analogous to the way the pistons in an internal combustion engine work. The work done is a combination of the pressure, the bore area of the piston, and the stroke velocity, or the displacement of the engine, is the product of those two things. If you want to extract power rather than drag from the wind, something attached to the ship has to move. That way it can do mechanical work on the moving thing, and that's how you can extract power from the wind with a drag device. If you have a way, and I'll talk about one way of doing that, if you have a way of extracting wind energy from the flow of the space plasma over the ship, you can use that energy to expel reaction mass with a conventional electric drive, or I happen to favor a linear accelerator type of thing because the workable efficiencies are very high, and at these power levels, efficiency is important. If you go through the idealized equations, again, the derivation of this at greater length is in the JBIS paper. The ideal case is for the exhaust velocity to equal the wind speed. Okay, now, with a moment's thought, I could have saved myself a month's of working out the equations, because that's intuitively obvious once you realize what's going on. My chat window will not stay open. There it is. If you think about this in the frame of reference that's co-moving with the wind, and you dump exhaust out, if that exhaust has any speed other than the speed of the wind, it is moving in the frame of reference of the wind. Obviously, you want the exhaust to have as little kinetic energy in it as possible. You want the kinetic energy to wind up in the ship. So it's intuitively obvious once you realize it that the optimum velocity of the exhaust velocity is equal to your wind speed. Now you have to pay for the drag, right? You can't extract wind energy without drag. So the specific impulse is actually half the wind speed if you do that. And that's, that half just comes from the fact that propeller thrust or windmill drag is thrust times velocity, and rocket exhaust power is 1/2 thrust times velocity. So the difference between those two is 1/2 times the velocity. And that gets you the following mass ratio equation, which is the wind drive analog to the Tsiolkovsky rocket equation. The mass ratio it takes to do a maneuver is your initial wind speed plus the change in speed squared divided by the initial wind speed squared. And again, I went through months of derivation to realize what should have been obvious at a glance once you get through the math. That's just conservation of kinetic energy, right? We aren't actually adding in the frame of reference that's co-moving with the wind. All that's going on here is you start with a heavy ship that has a certain amount of kinetic energy in it by virtue of its initial wind speed. You end up with a light ship, and all the exhaust that you dumped out is at rest with respect to the wind. Okay, so kinetic energy is conserved. If the ship starts heavy and it ends light, and it has the same kinetic energy when it's heavy and when it's light, kinetic energy being 1/2 mv squared, if m goes down, v has to go up. And it goes up as the square root of the mass ratio, because obviously it has to work that way. But what's interesting is in a lot of applications, particularly for maneuvering inside the solar system, nature grants you a very high initial wind speed, right? If you leave the Earth and get out into the solar wind, you have instantly acquired 400 or 450 kilometers a second of wind speed. So if you want to make maneuvers of only 100 kilometers a second or so, they're almost negligible compared to the initial wind speed. So I'll give you an example. Suppose you start from Earth and you want to go out to Neptune. Okay, well, you use the plasma magnet to get going at some speed less than the wind, something modest like 150 kilometers a second. Then you get out to Neptune, and now you want to thrust towards the sun in order to brake. Okay, well, your initial wind speed now is about 300 kilometers a second. You're making a delta V maneuver of 150 kilometers a second. That's a mass ratio that's only about 2.5. It's nothing. It's like a satellite. It's not like a rocket. And that gets you to Neptune orbit in a year, which I think ought to be useful. Now, okay, I don't want to, there we go. It's just impossible for me to leave this. I'm going to skip that because that's probably a little more confusing in terms of the rest of the talk. This is another thing to give you a sense of how do you pull energy out of the wind with a drag device. This is a cup anemometer in diagram, if you've ever seen one, the thing you use to measure wind speed with at weather stations. Okay, how that works is the cup spins, it's just a drag device, but it has a different amount of drag when it's going downwind with the wind blowing into the open cup than it does when it's going upwind with the wind blowing into the curved part of the cup. And that difference in drag, whether you're going downwind or upwind, means there's a difference in the amount of mechanical work that's being done on the device on the two halves of the cycle, the downwind rotation and the upwind rotation. So in order to get mechanical power out of a drag device, two things have to happen. You have to be able to stroke it. There has to be a motion of the drag element. And you have to be able to modulate it. It has to have less drag going upwind than it does going downwind. So a way to do that with the plasma magnet is to have two sets of plasma magnet driving coils at both ends of a long tether. And first you energize the windward one, and then you transfer the magnetic energy through the tether to the aft one, the downwind one. And the superposition of those means the magnetic field appears to move from the front to the back of the tether. And then there's a third set of coils that is toroidal, that's curled up, so they don't produce a magnetic field external to the ship. And you run it three-phase. You excite that one, then the storage coil, then that one, then the storage coil, so that the external magnetic field isn't there while the current is flowing backwards up the tether to charge the storage coil. This looks back of the envelope like we can get accelerations on the order of 0.05 meters per second squared in the solar system. I got dinged on a proposal for saying, well, nobody can do a 10-kilometer tether, which is what the back of the envelope numbers involved. This is the 19-kilometer tether that was deployed on STS-75. I always include that picture now so people can't say you can't do a long tether. Incidentally, you place the mass on the tether so that it's always in tension. You have to do that, otherwise doing that as a rigid device would be impractical over that kind of length. How am I doing on time? Not too bad. Since you have this long tether and you have currents flowing through it, the logical thing to do is put drift tubes on it, because then the tether is your particle accelerator. So much angst is done on particle accelerators for propulsion about trying to make them minimum length. It's actually much easier to make them if you don't try to make the minimum length. If you let them be long, then the accelerating field potentials can be quite low. And it's obviously desirable to have variable specific impulse on this thing, because you always want the exhaust velocity to be close to the wind speed. This also has use in interstellar flight. I was not expecting that. In brief, right, I wear an advanced propulsion hat that goes beyond my own work, where I'm trying to look at the whole field and kind of survey useful options as part of my work at Tau Zero. And it turns out there's actually quite a number of good ideas for propulsion systems that'll get you up to a few percent of the speed of light. They just don't scale well to 10, 20, 30% of the speed of light. Things like fusion rockets or fission fragment or very advanced solar sail concepts or things like that. So what this lets you do is do something that's a little bit analogous to a discarding sabot in artillery. You can launch a heavy thing, the ship plus a lot of reaction mass, up to a few percent of the speed of light, and then use this trick to concentrate that kinetic energy in your actual ship, dumping the reaction mass out with the interstellar plasma wind being your source of power. You haven't gained any kinetic energy, right? The kinetic energy you started with is still the kinetic energy you end up with, no free lunch. But you don't care, right? If you start with a 50-ton ship, 48 tons of which your reaction mass, and you end up with a 2-ton ship going 20% of the speed of light, you're a happy camper. So that kind of brings me to the end of the published stuff. And I'm going to see if I can get that blasted chat window that keeps disappearing back. And then I will take a couple of questions, and then I will go on to the unpublished stuff, which I had to not put in the slides, because otherwise, when I check the little box on the paper that says, have you ever published this before, I'm going to be in trouble. Screw it. There, I'll turn the chat off. So any questions before I go on to the unpublished stuff? Kilopower, yeah, this is a natural, you do need excitation power to drive the coils. And the higher the specific power of the excitation source, the higher the specific power of the net ship. So for in the solar system, solar is actually useful enough, but for interstellar, you got to have nuclear. You can launch 100 tons to Leo right now. I mean, so what if it comes up in 4 packages? Mass, it's never been cheaper to launch than it is right now. Okay, so on to the unpublished stuff. So I will emphasize for you guys, please don't race ahead and put this in publication, because I'm still preparing the paper. And therefore I'm not putting this in slides. So I can say I haven't published it previously. Okay. Suppose, I mentioned earlier that there are plasma wave and other type ways to push on stationary or near stationary plasma, right? That's not new, that's not a new idea. And I also mentioned that that's not itself very interesting, because if you try to push into the wind, you're talking about very high power requirements because of the propeller equation. What happens if you put a windmill in the wind axis, a wind energy extraction device in the wind axis, and you use that power to push on the plasma at right angles to the wind axis? Okay. Now, in the direction that the propeller is pushing, there is no wind speed. The theoretical power for getting thrust in that direction is very low. So it takes very little drag. The windmill produces drag. It takes very little drag to get a great deal of lateral thrust. We just described a device that produces a great deal of lateral thrust for every unit of parasitic drag. In atmospheric flight, we call that a wing. It's a device that produces lifting flight with a high lift to drag ratio. It looks to me back of the envelope like liftover drags of about 10 might be practical that way. Now, the problem with tacking that somebody asked about earlier in the thread is, in order to tack, you have to have a keel, right? You have to have something that keeps you from getting accelerated in the direction of the wind. But a couple of really interesting things happen if you can get high liftover drag. One, in the inner solar system, inside of about 5 astronomical units, the wind is not steady. It has turbulence structures in it. That's been very quickly highlighted by the Parker Solar Probe, although it's been known for a while. What that means is, on short time scales of hours, the wind direction is variable. So if your liftover drag is high enough, you can, in fact, tack. And the stabilizing influence is the inertia of the ship. You're changing your direction of thrust fast enough that you don't have time to get blown in the undesired wind direction. Your own inertia prevents it. It's not the Parker spiral. That I used to think that too. The Parker spiral changes the direction of the magnetic field. It has a relatively small effect on the motion of the ions themselves. But the turbulence in the solar wind caused by the fact that the sun is hardly steady does cause these kinds of variations. So it does look like you can tack in at modest velocities of tens of kilometers a second. But in the inner solar system, that's actually quite a lot. The part that I'm really psyched about, and I have to credit, oh God, I'm blanking his name now. The guy at McGill, Andrew Higgins, who put me onto this idea, is if you have a gradient in wind speed, you can bounce between the two of those different regions of wind speed and gain energy. It is, in a sense, an elastic collision between two regions of different wind speed. And this is called surfing if you do it with a surfboard. It's called soaring if you do it with a sailplane or if you're a bird. This is how those kinds of vehicles can gain energy, by moving between regions of different currents. We happen to have such a region that is steady and predictable at the edge of the solar system called the heliopause. The solar wind stays very nearly the same speed out to the heliopause because it's supersonic, and then fairly abruptly in the heliopause itself breaks down to effectively nothing over a region that's only a few astronomical units thick. Therefore, if you have high liftover drag, you can surf across the heliopause boundary and gain energy up to about your liftover drag divided by pi times the speed of the wind. Since the speed of the wind outside the plane of the ecliptic is about 750 kilometers a second, that gets you up to about 0.6, 0.7% of the speed of light with no propellant spent, which would be useful, particularly as the first stage of a multi-stage acceleration system for going to Alpha Centauri. And then the last thing I'll tease with, and then I will either end early or take questions, is something I've just, in the last month, started getting interested in, is can we pull this trick with one more layer if you have something like an advanced nuclear reactor on board, can you use the lateral thrust propeller, the propeller lateral to the wind, to gain velocity in a spiral in the inner solar system? That is, in principle, effectively infinite lift over drag, because you paid for the drag with the power that came out of your reactor. And that might lead to some very, very interesting maneuvers. I've already, just by playing around with this in Excel, got a trajectory to Mars that lets you do a 6-month round trip. About a month and a half there, about a month and a half stay, and about a month and a half back, which would be really, really useful, because you wouldn't have to expose astronauts to the space environment for years at a time in order to get to Mars and back. So the real takeaway again is not just these particular ideas that I'm talking about. These are just scratching at the iceberg. The real point is space is not empty, right? You do not have to figure out how to push on the vacuum. Pushing on the vacuum or pushing on the fixed stars or pushing on the frame of reference is really exciting from a physics perspective, because it would address very important questions about what are frames of reference, what is inertial relevance, it has deep implications for the physics. But if what you want is just propellantless propulsion, the plasma is already there and no new physics required. That's it.
Okay, great. Thanks, Jeff. Are there any questions? Because right now I'm not seeing our next speaker online, so I was really hoping for questions.
I hate to run. I didn't want to be the reason that you run further behind, so I tried to zoom through things a little bit.
No, you perfect. You were smack on time. In fact, you've got 5 minutes to go still, so you were perfect for question time.
So how does it scale?
In response to this, there was a question here about doing a small sat. I cannot believe that nobody's tested this in a small sat yet. It's just not that freaking hard. I've been evangelizing. I don't know if you ever saw the video. There's a funny video online about the first follower effect. And this is not my work. I just got excited by it. But I'm trying to be the first follower to run around and tell everybody, isn't this neat? Because if enough people realize that it's neat, maybe we'll get permission to fly it. I have put it in a couple of NIAC submissions and other things like that. So far, it hasn't been selected. As you are well aware, there are simply not that many sources of support for advanced propulsion work. I am cautiously optimistic that the AIAA technical committee that I'm now have gotten some people excited about this is going to get a chance to talk to the National Science Foundation about, are there new missions that could be enabled by advanced propulsion that are on the NSF's wish list? And maybe if they get to that level of visibility, we might get some things started. Because it's just not that hard. If I got ULA to agree that if I could come up with a mission, they would fly it for me for free as a rideshare payload, because there's no explosives on it. It's just, and you could test it with solar cells in the inner solar system, and it doesn't scale down to CubeSat exactly missions so well, but it's certainly a small sat in the 50 to 100 kilogram class. And it'd be neat. It's kind of a Sputnik mission. It'd be neat to do a rideshare payload, kick it out, and watch the beep, beep, beep leave the solar system at 120 AU per year. Even if it ran out of power after it passed 5 AU because the solar cells weren't useful anymore, you'd have proved everything you needed to prove. But so far, no funding.
I would like to ask a question. How big do the sails have to be to reach those solar wind velocities in the solar system? Or how do you capture that much momentum? I do have a fundamental question that the solar wind, the interplanetary, interstellar medium are like 0.1 proton per cubic centimeter. So very rarefied. So if I just think naively, where's all this momentum coming from? Everything's moving fast, but there's not much of it.
Yep.
So
that's the fundamental challenge. You're absolutely right. So in the solar, the interstellar medium is highly variable. I think if I quote numbers for that, I'll get it wrong. And besides which, we don't actually know the density of the G cloud, which is kind of important. But in the solar system, the dynamic pressure, the 1/2 rho v squared of the solar wind at 1 AU varies quite a bit over time, but it's in the neighborhood of a couple of nanopascals, 2, 3, 4 nanopascals. Part of the reason it's variable is the solar wind density is highly non-uniform, and it varies in a manner that's anti-correlated with the velocity. So the dynamic pressure is actually slightly less variable than you'd think, because the wind tends to be thick when it's slow and thin when it's fast. So you take excitation coils that are on the order of meters to 10 meters radius. That's big enough that the ratio of your thrust power to your excitation power is on the order of 100,000. The bigger the coils, the bigger the multiplier. That means that with hundreds of watts to kilowatts and 10 meters of radius of coil in the inner solar system, you get when the magnetic field is fully inflated, you get a magnetic field radius on the order of 100 kilometers of radius. So your interception area of the magnetic field is on the order of 10 to the 10th square meters of intercepted field. 10 to the 10th square meters times 10 to the -9 pascals is 10 newtons. And I've slipped a couple of factors of pi and things like that in there, so it actually comes out closer to 100 newtons for that particular worked example, which is not too bad for no propellant spent.
And you're saying it's the force between the magnetic field generated on the craft and the magnetic field entrained in the solar wind?
Negative. The magnetic field entrained in the solar wind is actually a parasitic, undesirable effect. What you're doing is you expand the rotating magnetic field coils make an electron current in the plasma.
Mm-hmm.
You choose a frequency for rotating magnetic field that is close to the electron gyro frequency of the exposed plasma.
Mm-hmm.
In other words, you pick a frequency that the electrons in the plasma can follow.
Mm-hmm.
That frequency is, by definition, way higher than the frequency that the ions can follow, because the ions are heavy compared to the electrons.
Mm-hmm.
That means to the ion flux that's coming in the solar wind, all they see is the steady field caused by this circulating electron current.
Mm-hmm.
Now that circulating electron current will expand until the magnetic field pressure of that field is balanced by the dynamic pressure of the ion pressure of the wind. So the solar magnetic field doesn't actually come into it unless you start talking about velocities that are very close to the wind speed when your dynamic pressure starts dropping off to nothing. Does that clear it up any?
I guess sort of the mechanism, but you're still saying somehow this ball of magnetic field is picked up dynamically in the flow of the solar wind, right?
It's pushed on. The solar wind pressure pushes on the magnetic field. The magnetic field pushes on the coils. The coils push on the ship.
Mm-hmm. And so its cross-sectional area is effectively the size of these magnetic fields.
Yes.
Intercepting that much momentum flux.
Yes. And the basic principle, you can see all the calculations of this in Slow's papers. Mm-hmm. And it got as far as Slow demonstrating the exterior field, with the device that was about this big, like an inch. He got the exterior field to 4 or 5 inches inside his vacuum chamber of non-conducting material with the ion thruster simulating the solar wind pointed at it. So.
And did it pick it up? That was the thing I was struggling with.
Yes.
Is would it pick it up?
Yeah, it actually, he actually pushed on it in the pendulum balance to make sure that the interactions actually are all mechanically attached through the fields pushing on each other.
Yeah,
the fact that it works is not surprising because it's the same way that the torque, gets reacted from an electric motor onto the rotor. But it's one thing to say that it should work, and another thing to say that it does work.
Yeah. Well, thanks for that explanation.
I encourage you strong. The NIAC reports from Slow's work are easy to find online, and he goes into this in great detail with some beautiful pictures of this thing operating in the wind tunnel.
Yeah. And I know the solar wind is magnetized, so everything is sort of tied together. I just wondered if it would just interpenetrate like ghosts and not pick it up at all. But I guess his calculations show that, they are going to interact. And I'll have to look at that. I'll look forward to those references.
Yeah, what makes me feel fairly confident about this is, unlike a lot of the other ideas of people have had over the years about pushing on the plasma, is you're not really asking anything to be confined by the device except the electrons. Those are the easy to grab onto thing. You're not actually confining the ions of the solar wind. You're just scattering them, which is the thing that magnetic fields do fairly well. Yeah. So there have been a lot of ideas in the past for some kind of magically high confinement plasma reaction systems that neither I nor anybody else got all that excited about. But this one, I mean, when I ran across it, I'm an electrical engineer by training. When I ran across it, I went through this and I said, I can't figure out why this might not work. I couldn't figure out any reason why it shouldn't work. And so that's a lot better situation to be in than I hope it does. Yeah. But, the acid test is you got to fly it in space. Nobody's going to make a 100-meter vacuum chamber to test the next scaling step. And it'd have to be a non-conducting vacuum chamber anyway, because otherwise the currents in the walls of the vacuum chamber will interfere with the measurement you're trying to do. So given that this can be tested at 100-kilogram scale, the thing to do next is try and fly it in space.
Yeah, it's a nice idea. Thanks for sharing it.